Hello everyone, welcome to the tutorial for NPTEL course Programming Data Structures and Algorithm. This is the tutorial for week 6. As always, we'll be looking for some problems and the approach to solve those problems, and we'll try to uh, see how can we code the problem, and we'll see that we'll analyze the output produced. So first problem is creating a binary max heap from the given sequence, and we'll also see that how can we remove the root and add another node, uh, and still retain the natural shape of the heap. And we'll also look at the heap sort in the same example. So as we have already seen in the class that it's a special type of binary tree. And in, if we talk about max heap, so here is the example of max heap. So we'll talk about it in a bit. So for max heap, a parent should have larger value than its children on the either sides. So if we look at this example, so the root node is 17. So it has two childs, that is 15 and 10, and the value associated with these two childs is lesser than 17. So in both the cases, it is lesser than 17. Whereas the child of 15, for them, the value is lesser than their parents, which is 15. And and similarly for 10, for node 10, the child which is 7, it has value lesser than 10. So this is an example here. This is an example of max heap. In case of min heap, this would be opposite. The root would have the minimum value in the whole tree. We'll look at it a bit later. Now, if we are looking at a node I, then the parent of this node will be I minus 1, uh, I minus 1 floor division by 2, and the children's left and right will be 2i plus 1 and 2i plus 2. So let's say for now that for 15, let's say, so it's 0, 1, 2, 3, 4, 5. So it has total 5 nodes. So I'll remove everything else except the node index. So 0, 1, 2, this is 3, 4, and 5. So if we take the node I, so its parent will be uh, a, a node for the node 15. Its index is 1, so its parent will be 1 minus 1 divided by 2. So that will be 0. So its parent will be 0, as we can see here, and its two child will be 2 into 1 plus 1, that will be 3, and another child will be 2 plus 1 plus 2, that will be 4. 2 into 1 plus 2, that will be 4. So 3 and 4 are its child. So we can see here with the example. And another example is if we take this node with associated value 10, so its parent will be 2 minus 1 floor division 2, so that will be 0. So its parent is 0. And its child, so it has only child, that is a left child, so that will be 2 into 1, uh, sorry, 2 into 2, because it's a second node. So 2 into 2 plus 1, so it will be 5. So its left child is the fifth node, as we can see here. Now, left node, they must be completely filled before we can start filling out the right node. So we can see here that we started with root 0, then we went to node 1, then we created two of its childs, that is node 1 and node 2. Then we started with the left node and we filled its both the childs, and then we went to fill in the child for node 2. So that is why the index for after the index for the child of uh, childs of node 1 was 3 and 4, and the child of node 2 was 5. So, and if we follow these set of constraints, we can create a binary max heap. So I'm saying max heap because the maximum value is for the root here, and as we drop down to the consecutive children's, then the value is going to drop with respect to their parent. Now, if we want to delete the root, then delete the root or insert any node, then we must maintain the structure of a heap according to the constraints that we have discussed. Then only it will be called a heap. If we do not maintain the if you do not maintain the structure, then it will simply be a binary tree. Now for sorting using sort heap in loop, we will I mean we will look at it in a while, but just for the sake of uh, what we are going to do is so in loop we'll switch the root with the last element. So root will be the maximum value element, and the last element will be the minimum value element. So we will switch them, and then we will again rearrange the heap with respect to the root node, so which has the minimum value now after rearranging. And we will follow this process again. We will again change this root element with the remaining remaining next I mean remaining the last element of the remaining length. So I mean in the first iteration, when we exchanged the value of root with the minimum, then uh, we will just set aside the last value, and with the remaining value we will again do the process. So this is how we will be arranging our input data in the form of min to max sort. So we'll see this through a computer program that is written in Python. Yeah, so this is the program. So basically this function heapify simply I mean, Heapify helps us to uh, it helps to rearrange the node so that the heap structure is maintained. So as we have already discussed, so basically heapify function will take inputs as it will take input sequence, then it will take the length of the input sequence as an input, and the particular node at which heap our we want to heap our input sequence. So now for the time being, we are assuming that this particular node is the maximum value node. So any value corresponding to this index is a maximum value, so that we are assuming. And we are then its child will be left child will be defined as 2 multiplied by I plus 1, and right child will be 2 multiplied by I plus 2, as we have already seen. Now we'll check the validity of the node, whether this node exists within the length of input sequence or not. If it does, then we will also look whether the value associated to max value node is lesser than a value associated to left child. If so, then we will assign left child as the max value node. But if that's not the case, then we will check the same for the right value node, and if the value against the right value node uh, is lesser for the max value node, so we will assign the max value node as right child. Now if any of these is true, so it means that the max value node is not I now. So if it is I, then there is no issue. But if our max value node is not I, in other words, so either left child value associated to left child was greater than max value node, or value associated to right child is greater than max value node. So in both the cases, max value node will not be the ith node. So as we initialized earlier, so we will we will simply assign the max value node to be the ith node. So I mean, as we have already assigned the if any of the child was max val node, so we have assigned the max val node to be that child node. So now we are assigning I to have the value, the maximum value associated to that particular Maxwell node. So now the Maxwell node will be the ith node, and we will check this again by running this heapify in the recursion. So next we will be so this is how we would be we will be heapifying the given node. So or we will try to maintain the structure of the heap for the given node. Now we'll see that in the I mean, if we have such a function that can maintain the structure of a heap, so with the help of that function, how can we sort a given input sequence in a increasing or decreasing order? So now we are going to define another function, that is heap sort. So heap sort will take a simply input sequence as an input, and then uh, we will iterate over nodes. I mean, the length of the sequence, floor divided by 2 minus 1 to 0. So, I mean, for the reason for the same is, let us say we have, so I'm writing here indexes, not the values associated. So let us say this is 0th index, first index, second index, third index, fourth index, then this will be fifth index, sixth index, seventh index, eighth index, ninth index, 10th index, 11th, 12th, 13th, and 14th. So let us say we have a we have a binary tree structure, something like this. So but remember, as these are the indexes, so value corresponding to that I have not mentioned. So there could be a possibility it is not a heap, so it can be a simple binary tree where the value associated with zero index may not be max or min, it could be any intermediate value. And this is, we are yet to rearrange this. So if we look at this, we have total 15 elements here. So length of this particular heap, so what we are calling nodes there, so that is 15 in this case. So if we do 15 floor divided 2 minus 1, so that will be like 15 floor division 2 will be 7. 7 minus 1 is 6. So basically, this sixth node, we will start our calculation was from sixth node. We will heapify this node. So after heapifying, we will have the correct structure that we are expecting here. Then we will iterate and move to fifth node. We will correct here. Then we'll move to fourth node. We'll correct here. Then third node will correct, and then we'll move to second node will correct, first node will correct, and this is how we'll be correcting our heap structure. So after running this function, and a binary tree will be converted to a heap, a binary heap. So now after converting to a binary heap, our this particular heap, after applying the this heapify over these iterations, we will heapify this this tree, and after heapifying, root will have maximum value, and last node will have minimum value. So now we will again iterate from so as we already know that in Python our index starts with 0, and the last index is total length minus 1. So that is why we are the total length is in this case it is 15, but the last node is 14, which is 15 minus 1. So that is why we are starting our calculation from uh, we are starting our calculation from the last node, and we are going up to the first node by stepping down by one in every iteration, and we are replacing the value associated to root node with that iterative index. And this is how so let us say our data is something like, so it's a zero index, first index, second index, third index, fourth index, fifth index. So rather, I would say, let us say I have a list. So it has some data. So the data would be like LST 0 plus LST 1 plus LST 2 plus LST. So for nodes, I am writing n here right now. So it would look something like this. So this will have minimum value, and this will have maximum value after after heapifying. So we will rearrange. We are just switching. I mean, in this step, what we are doing, we are just switching this value. So we are making it like LST n minus one, and then everything else will remain same. LST1, LST2, and so on, and the last element will be LST0. Okay, then we will heapify about this first node. So we'll heapify about this first node, and the first node and its child will be corrected. First node and its child will be corrected, and we will get a new list. So what we or a new sequence, and in next iteration we will be as in next iteration we will be having I as nodes minus 2. So we will be switching the value at 0 to nodes minus 2 node, and we'll keep on doing this up to node 1. So um, when we process this our data, you can see that every time we were getting a maximum value after heapifying at node 0. So we are switching it in every iteration. So the maximum value goes to the last index, and the value just then the value lesser next to it goes to second last node, and second last index, and value lesser to that goes to third last index, and so on. So this is how the sequence from max min to max is maintained during these calculations. In next and we have heapified our function, or we have done the heap sort. Then next idea was to uh, delete or add a node. So now in next problem, sorry, in next function, what we are going to do is we are going to, let us say we have our values like let's say we have a max heap which looks something like 12, then 8, 6, maybe 3, 2, this is 4, 5. So let's say we have this heap, and we want to insert a value which is which may be 10 or maybe 24. So if we are inserting a value 10, so this 10 is actually greater than 8 and greater than 6, but it is lesser than 12. So it should replace one of the childs here, because it should come under this node 12. Now, if we insert value 24, so 12 is lesser than 24, hence 24 should be our new node, sorry, new root. So that is for insertion. And if in this particular, so basically, if we are inserting, this is for insertion. And if we want to delete the root node, so if we want to delete the 12, so if we want to delete the 12, some new value should replace 12 as a root node. So if we look at this small heap, we can simply say that 8 should be replacing 12, and our new heap should, it I mean, we need to heapify it so that we would know how it's going to look like. So for that, we are going to write the del top node or del root node function. So I have given name here del top node. It will take input sequence as the input. Now, as you know, after deleting the node, we also need to update the length of the input sequence, because it is also going to change. Because if we have data that has length 0, 1, 2, 3, 4, 5, 6, so total length is 7, and if we want to remove one node, so the length will also decrease and it will go to 6. So as we want to as we want to change the immutable sequence, sorry, immutable uh, data. So for that, what we are going to do is, if you want to change the immutable data, so for that we will be defining nodes to be global, and then processing this further, we will be able to change this. And we can get the output because of that change. So now, uh, what we are going to do, we first of all we need to heapify our data, if it is not already, if it is not already a heap. So this function we have already seen. Then what we will do, we will simply exchange, so last element would be like, from the sequence. So at last index, there will be the last element. So we will replace the input sequence with the last element. So now last element would be, um, you know we will replace the, sorry, we will replace the input sequence with the last element, and we will delete the last element. So whatever it was, we'll simply delete it. Then we will update the node, because so I mean, if we want to have a look how it's going to look like, I'll just tell you what's the procedure actually that should look like here. So in our case, where everything is given, okay. So in this particular case, this already is a max heap. So the last element in this heap is going to be 5. So what we are going to do, we are going to exchange this element here. We will, this 5 will be placed here in place of 12, and then we will heapify it. And we will place 5 here in place of 12. We will delete this node. So then we will be having something that would look like this. Then we'll be having something that is look likely, and then we will heapify again. Then we will heapify again. Heapify, so to get the proper max heap. So first we need to heapify our list, and then we will exchange the root element, because our idea is to remove the root element. Then we'll remove that root element. We will change the length of the list, because after removing, the length will be decreased by one. We'll do that, and we will again heapify proper uh, to get the proper heap structure. Now, similarly, for inserting a node, what we are going to do, let us say we want to insert 12 here. So what we are going to do, will simply we will place it in the form of, let's say, if we have an input sequence, so we'll not heapify at the start. So we'll have an input sequence. So input sequence could look like maybe 5, 3, 2, 8, 4, 6. So we'll insert element. So as we were to insert 12, we'll insert element at the last by using append function. As this is a list, we'll simply be appending. So after appending, we will also add one node, because earlier the length was 1 2 3 4 5 6 6, but we have added one more element, so the length has become 7. So the nodes which was earlier lesser. So for this node, for this data, the node is going to be the length of this sequence. So we are going to update that length for the data, and then we are going to again heapify this to get the proper max heap, as we were expecting. So this is how we are going to heapify our data, or we are going to sort the data using the heap sort, or we can delete the root node or insert any node we wish. So that's how we are going to proceed. We'll try to uh, see how the output is going to be generated for the same. So yeah, we'll try to run this code, and we'll see how it's going to work out for us. So uh, yeah, we'll list the files there. So the file is heapsort.py. So we'll simply say Python heapsort.py. So now, as our input data, if we see, so we'll see how we have provided the input. That is also important. So our input data was 3, 2, 12, 16, 2, 3, 23, 6, 12, and then we ran this we ran this script to heapify our list. So now if we look at our list, it looks like 23, 16, 12. So we will see whether it's a proper heap structure that we were expecting or not. So for that, we'll start here. So our heap data is 23. So I'm writing the value. I'll not here. I'm writing the value. I'm not writing the the index for the element. So we are directly writing the value. So it's 23, then 16, 12. Then we have 12, 2, because we need to fill in the right node first. Then we'll go to left node. This is 3, 3. Then we'll fill the left node that is available here. So this will be 2. So 23, 16, 12, 12, 2, 3, 3, 6, 3, 3. So there will be a 6, I think. 6 and 2. Okay. So 1, 2, 3, 4, 5, 6, 7, 8. And entries were 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I think we missed some values. So we have 23, 16, 12. Then we have 12, 2. Then we have 3, 3. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so the values are same. It seems like the heap structure is maintained after running this particular function. Then after, if we look at the second, after we look at the second function, so for that we had given, we had given a separate input. If you see, we have again given an input so that, we are not going to start with the preserved heap structure. So I mean, so we want to see whether after deleting, whether it properly does change the heap structure or not. So if we were to run this this the next function, delete root node function. So either we could have, after heapifying, we could have simply use the output list. So if it is a heap, it's already a heap, so it does not matter, but here we wanted to check whether this function is properly serving its purpose or not. So for that, we have given a sequence. We have given the same input sequence that we had earlier given. So we are not entering the updated sequence in here. That was the max sequence. So now we are running this function delete top node. So for output for that, we got like 23 was removed, so that was the top node, and we got the remaining part like this. So we will check whether this represents as a heap or not. So if you are thinking that after we can simply remove this 23 and 16 will go at the top and the structure will be preferred, that's not how it's going to work out. And we can simply see here that here the sequence from 16 is 16 12 12 2 3 3 6 2, but here it's 16 12 12 6. So this 6 from here has come has changed its position with with you know it has changed its position with the 3 or something. So we will see whether this is a proper heap structure or not. So so the root is 16, then 12 12, then we'll have 6 2, then we'll have 3 3, then we'll have 2. So we can see this is a proper max heap structure as we were expecting. So it seems fine. Then we will again input the original sequence, and we'll see whether it's sorting the data properly or not. So we can see that it has properly sorted the data. So as maximum value is at the end and minimum value is at the as at the start, and as we are increasing the index, the value associated to it is increasing. Now we have tried to insert a node 56 in here, and we'll see if to the sorted sequence. So this was a sorted sequence, but uh, if you see, I mean, here before the insert node function, we have not again given the input sequence. So now our input sequence is the sorted list that we have just seen. So that sorted list we will be inserting 56. So as we have seen, it will be inserted at the last, and then heap structure will be preserved using heapify function. So the output of this, we will simply look whether it's okay. So the output is 56, 23, 12, and so on. So we'll check whether it has been properly preserved or not. So it's 56, then we have 23, we have 12, then we have 16, 6, then we have 3, 12, we have 2, 3, then we'll be filling it. The right one is 2. So we have total 10 element, and we can see that the heap structure is preserved. So in next problem, as you might have observed, I had called it problem 1A. So second problem is related to that. So like in first problem, we went for max heap. In second problem, we'll look how we can rearrange a given data in a min heap form, and and we'll also see that how can we sort using heap sort. So we can, I mean, in this case we'll try to rearrange the data from max to min, as in a earlier case we tried to rearrange the data from min to max. So as we have already discussed, in case of min heap, the node should have the root node should have minimum value, whereas as we go below, so as we go below to the root node should have minimum value, but its child should have value more than the parent node. So here we can see that the root node, which is a parent node, it has two childs 7 and 12, which are greater than 6. Then node 7 has two childs 10 and 15, which is greater than 7. And another node, that is 12, has another it I mean uh, it has uh, a child which has value greater than 12. But I think somewhere by mistake I have said that in case of max heap, that root should have maximum value. That is true, but the last element will have minimum value. It's not true, pardon me. Here, this is not true. So there can be other elements which have minimum value, but yes, the last element will surely have value lesser than the maximum value, because root has the maximum value. Similarly here, so in case of max heap, this was the case. In case of min heap, uh, root will be minimum value, but last element will not be a maximum value. So any element, any other element, than our a root node can have maximum value. So, I mean, this is I mean, by chance there, like in this case, by chance the last node has the maximum value and root has minimum value, but there can be a possibility that, the last node is not the maximum value in case of min heap. So we need to be careful about that. So I think by mistake I have mentioned that. But anyways, so we'll be using the same rules as we have discussed in case of max heap. In min heap, the root should be maintained at the minimum value, and as we pass on to its child, the value of child should be greater than the value of parent. So we are going to use the same, and for sorting, we are going to use the same concept. We will switch the root element with the last element, and then we will keep on doing this, we will keep on doing this uh, as the length of um, you know as we iterate over the decreasing length of the input sequence. So yeah, so our next code is for min heap. We have this code. So if we look at this, basically, I mean, just for the sake of you know just for the sake of differentiation, I have, for min heap, I have given the function name min heapify. Everything else remains same. So here, we will say that the assumed node is the minimum value node, and its left child is 2i plus 1, right child is 2i plus 2, that is going to remain same. we will check the validity of the left child, and we will check the we will check whether the value associated to min val node is greater than input sequence, I mean greater than the value associated with left child. If so, we will assign minimum value node as the left child. But if but you know if input sequence if the value associated to min val node is lesser than input sequence left child, then we will move on to next. Here we will check whether the min val node, I mean the input sequence associated to index min val node is greater than the uh, input sequence associated with with element right child. We will check if it is greater than, we will change min val node to be the right child. Now, if any of these above conditions checks out, then of course min-val node will not be the ith node. So what we are going to do in that case, we are just going to switch the position of ith node with min-val node. So our this condition gets preserved, and then we will use the recursion. So then for heap sort, as we have already discussed, what we need to do is we need to run our we need to iterate over the length nodes floor divided minus 1 to 0 by stepping down by step minus 1, and then we will run this min heapify function on respective nodes, as we have already discussed. So like if the length of the given data is 15, so last node will be 14, and 14 minus 1 is it is going to so the total length is 15, so 15 floor divided by 2 will be 7. 7 minus 1 is 6, so we'll start with the sixth node, and we have already seen for the data that is of length 15 how when we start with nodes floor divided by 2 minus 1 to 0 uh, by running this heapify function, we get the intended output, that is the heap structure is maintained. So that we have already seen, the similar thing is followed here. Then we will we will try to, as we have discussed, we will be exchanging, first we will be iterating over the length of the input data. So we'll be at the start the length I mean we'll be iterating over the elements of the input data. So we'll start with the last element, and we will move up to first we'll start with last element, and we'll go up to the second element, and we will keep on exchanging the zeroth element with the input, with the ith element, and then we will maintain the heap structure for the root element. So as we will shift our we will shift the last element with the root, we'll exchange the last element with the root element. So now the heap structure at root element may not be preserved. So of course it is not going to be preserved, so we'll try to preserve the root structure at the root element, and then we will again run this for next element, that will be nodes minus 2. We will again exchange the zeroth element with node minus 2, and so this is how we will be keep on pushing the smallest value to the last element, and second smallest value to the second last element, third smallest value to the third last element, and so on. So this is how max to min structure is going to be preserved. So we will with for the same input data, we will see that how our code is going to respond. So uh, yeah, so the problem, it is min heap dot py. So as we have already said that, first we are creating the heap structure. If you see, this is the input sequence, and then we are trying to create the heap structure from the input data. So we'll see whether this heap structure is properly uh, preserved or not. So, you know, okay, so the that we got is, output that we got is 2, 2, 3, 6, 3, 12. So we'll try to look whether it's in min heap form or not. So 2, 2, 3, then 6, 3, then 12, 23, then 16, 12. So we can see here that the root element is the minimum element. Then as we are moving below, the value of child is either equal to or greater than its parent. So, you know, so I mean, in a way, if we can see that the heap structure is preserved for the um, I mean, preserved as a min binary heap. So, and the next problem, I mean, next, we, uh, so we retained the same rearranged input sequence, and we have given it as an input to min heap sort. So I have not given this input sequence again. It's in its original form. So uh, this we have already seen that this is going to first heapify the data, and then it is going to apply the sorting. So, but our data is already heapified. So, if it were not, it would have heapify it. So, but anyways, so we'll see whether it has sorted our data from min to max or not. So, yeah, we can see it has sorted our data from min to max. So, in this particular problem, we have not focused on deleting the root node or inserting another node. So we have already discussed it for the max heap. I would expect you guys to do it on your own. So now we'll move on to next problem. The next problem is solving a Sudoku given Sudoku puzzle. So basically, in Sudoku puzzle, we have one large box, one large square that contains smaller sub squares. So it has like 1, 2, 3, 4. This is fifth one, sixth, seventh, eighth, ninth. So it has nine sub square, and all the sub square has, boxes 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the structure of the boxes, and the idea is we need to fill in a row or a column or a box uh, with numbers 1 to 9, and in a column or in a row in a row or in a column or in the box highlighted here or here or here, any number should not be repeated. So that's the idea behind this puzzle. So basically this is a puzzle in its original form. So yeah, this is a puzzle in its original form, and this is a puzzle problem. This is the solution of this puzzle. So you can see that in this particular box, none of 1 to 9 is repeated either here or here or here or here or here or here or in any of the row or the column. the 1 to 9, none of them is repeated. Okay, so but they can be repeated across this large diagonal, I mean large right, left diagonal or right diagonal, but they are not going to be repeated in in the given row or the given column or the given large box. So basically, if we talk about the indexing, in Python, as you know, the indexes start with 0, so it will be 0, 1, 2, 3, 4, 5, 6, 7, 8. So index for columns will be 0 to 8. Similarly for row, 1, 2, 3, 4, 5, 6, 7, 8. And for the box, so for the box, it should be like, if we are starting with 0, then for this particular, for this particular box, if we are starting with 0, then we will be iterating. For row, we'll be iterating from 1, 0 to 2, and for column also will be iterating from 0 to 2. So if we do that, we'll get all the elements. So like this is 0, this is 1, this is 2, and this is 1, this is 2. So so this is how we have the row and column structure. Okay, so uh, rather I would say, if we write it in row column form, so this is 0 0, 0th row, 0th column, 0th row first column, 0th row second column, first row, first row 0th column, first row first column, first row second column, then third, then we have second row 0th column, second row first column, second row second column, and so on. For this, it should start with, it will be starting with third column and 0th row. So if we are like 0th row and third column, then we'll iterate over 0 to 2, we'll add, so we'll be getting it like 0 0 1 2. So row will go from 0 1 2, and column will go from 3 uh, 4 5. So if we do that, we will have all the elements in here, and this is how we can move over the elements of the elements of Sudoku puzzle. So this principles actually, this ideas we are going to implement in case of the solution of this Sudoku puzzle. So basically, just to initialize, just to initialize the problem, we will be like representing 0 as 0 in place of unfilled element, and then as the problem progresses, we will be filling, we will be replacing 0 with the help of elements from 1 to 9. So whichever fits in properly to solve the puzzle, that will be entered in. And as we have discussed, they should not have any, the entered element should not have any disagreement between rows, across rows or column, or the respective subsquares, as we have already discussed. So, and if if during the solution we realize that the filled box, it has some wrong entry, then we can backtrack that box with 0 and start over with remaining entry from 1 to 9. So we are going to approach this problem uh, as uh, as we have already discussed. So basically this problem, if we want to check whether a particular element, it is filled correctly or not, so for this, the input to our function is filled function I'm going to use here, just to check whether uh, a particular element in a given row or column, even given row and column, is filled correctly or not. So let us say in first row and second column, so the element prob 2 comma 1. So if we talk in terms of, so 2 comma 1, so first row is, this, so I mean zeroth row rather we would say, because indexing is start in Python with 0. So zeroth row and first column, so zeroth row is this and first column is this. So this element basically will be 0 1. So this element will be 0 1. So we will say, okay, this is a 0 1 element, this is a 0 2 element, this is a 0 0 element, and so on. So yeah, so we will check for a given row and a given column the number that is entered in, whether it is correct or not for our given problem. So problem basically would that we would enter it, it would be in a form of a list. So I'll just show you how it is going to look like. So problem would look like a list. So it would have 9 rows and 9 columns. So 9 rows, so first row, second row, third row, fourth row, second sorry fifth row, sixth row, seventh, eighth, and ninth row. And similarly we'll have first column, second column, third column, fourth column, and so on. So that's how the problem is going to look like, and we are going to look for the elements in it by the row and column, and we will check whether the entry filled in here, that is equal to n, whether it is correct or not. So box length, basically the box length is 9 here. So we will define it later. So as you know, it's a 9 cross 9 puzzle. So box length is 9. So it has 9 number of rows and 9 number of columns. So for I in range, so we will check in a particular row whether across in a particular row whether this number n matches or not. If it matches with the with value in some other box in the same row, then we are going to return false, that this is not filled properly. Then we will if our if this passes across the row, then we will check across the column whether it passes or not. If it fails, then we'll say, okay, this is not the correct element to fill in. But let's say that it passes across the row and passes across the column. So for example, if we check in here, let's say I want to fill some number here. So let's say I feel like I should be filling maybe 1 here. So one does not have any agreement here, because it is repeated in the same row. It is repeated in the same column, and it is repeated in the same box. So we cannot fill in 1 anyhow. What if we filled 8 here? Then 8 is neither repeated here nor repeated here, and it is also not repeated in the same sub square. So there can be a possibility that 8 can be filled here. But if if we try to fill maybe other than 8, we try to fill maybe 5 or 4. Then if we try to fill in 5, then 5, it does not fail across the row, but it fails across the column, and it also fails across the I mean within the given sub square. So we need to be careful. So all these conditions need to be checked so that a particular number, if it is filled in properly, is passed or not. Then we will write another function where where we'll be checking whether, as we are moving from 0th row to the last row, and 0th column to the last column. So if during the solution of a problem we reaches to the last row, and we reaches beyond the last column, then we can say our puzzle is already solved. And if the solution is correct, then it will return true. Or if it's not correct, it will not reach the last column, and it will return us false. Then we will also check that whether this column, whether it has passed the last, if you know, if this particular thing is either passed or we have not reached the last row. Okay, so then in that case, if we have reached beyond the last column, then we will be, starting from, we will be updating the row, and we will update the column to the 0th column. So when we have started here and we filled all the all the columns in this particular row, then we can say, okay, this row is filled, and we will go to the new row, and we will start with the 0th column. So that's what it actually says. And then we will check whether this particular row and column, whether it has a value greater than 0 or not. If it has a value greater than 0, then we will move to next column. Then suppose at a particular cell, we don't see the filled value, then we are going to check that whether number from number 1 to 9, which number fits in here. If any number fits in here, we will assign that particular number to that particular cell, and we will check to the next column, and we'll keep on moving accordingly. Now if this particular, if after this we realize that whatever the value we had filled in, it's not right, it is wrong, then what we are going to do, we are going to backtrack our solution. We're going to backtrack our solution for that particular grid cell, and we are going to update it to 0, and we will again start our calculation. And if somehow our puzzle does not have a unique solution, or does not have a solution, in that case it should return a false. Now we have just written a printing function, so that the puzzle looks, I mean, so the solution of the puzzle and the problem itself looks like in a Sudoku form in some way. So for that we have written this function, and now we can either give the puzzle in this commented form, or we can give the puzzle, in a text file. We can write it like this. We can, after giving every entry, let's say in 0th row, after first entry we'll give a space, second entry is space, third entry is space, and so on. Then after last column in that given row, we'll move to next line. We'll follow the same, and this is how 9 cross 9 puzzle can be written in, I mean, in this particular form, so that we can solve it using this particular uh, uh, a reading file method. So we have discussed this already, so that is why I have chosen this method. So, and here, as we know that when it will be reading the line, it will read it as a string. So we have split the string with the empty space, so that is already there, and then we are converting it to a integer. So this is how we will be having first row, then second row. So as we are moving across the lines, we'll be having consequent rows. So this is how our problem will read as the stack of rows. So first row, second row, third row, fourth row, fifth row, sixth row, seventh row, eighth row, and ninth row. So this is our problem will be read, and we can produce the solution. So first of all, we have printed the problem. So I mean, how it looks like in our, uh, in our I mean, in our Sudoku lookalike output, and then we have also tried to solve this problem, and and if there is no solution to the problem, if the function returns false, so here you can see, if the function returns true, then we are going to print the solution, but otherwise we are going to simply return that no solution exists. So we will see that how it's going to run. So let us say this is a Sudoku puzzle that we have seen um, in one of the files. So we'll see if the puzzle is that we have seen in this particular file in here. uh, okay, so it was okay, so this was problem text one, so this one, so this was our problem. So it looks like this, and the solution to this problem is going to look like this. Similarly, if we can choose some other problem as well. So let's say we are, just to save time, I have taken these problems from sudoku.com, so you guys can try. I'll give this code in the comment of the video. You can look at this solution. You can try different problems, Sudoku problems, and you can check the solutions of the problems using this particular code. So for that, what we need to do is we need to just change the input here. So we'll save it, and then we are going to run this again. So now our new problem, which should look like this, and its solution that is produced using the function that we have written to solve the Sudoku. So in Sudoku you have in Sudoku.com you have many levels of Sudoku puzzles. So starting from easy to evil. So evil is the most difficult level, and easy is the easiest level. So any of the level you can start with, and within less than a second you can have the solution of your Sudoku puzzle. So this is all.